Hello, I'm Walter Lockhart, and today I will present SOLO, which stands for Small Orbit, Large Orbit, Peak Power Tracker Control. Let's look at a battery clamped PPT power system as shown here. This is done for simplicity. Show a solar cell array on the left side. This feeds a DC to DC converter. The converter output is directly connected to a battery, which we would call a battery clamped power system. So we have the battery string, have a load resistance, we have a current sense for the battery. The current sense feeds the SOLO PPT controller, which in turn controls an error voltage back to the DC to DC converter to control the system. So this is what we're talking about, a battery clamped power tracking system. The DC to DC converter shown here could be a buck, a boost, a buck boost. It could be resonant, quasi-resonant. It could be isolated. The topology of the DC to DC converter is not important for the SOLO controller. What I'm showing here is simply how the SOLO controller would connect to a DC to DC converter, and that the system is designed for a battery clamped setup. Let's look at the solar array characteristics used in this example. Here we have a solar array curve showing the voltage and power from the solar array cells. Characteristics include a 56 volt open circuit voltage, a 42 watt maximum power point, a 48 volt maximum voltage power point, and a short circuit current of 9/10 of an amp. Of course, all of these characteristics are not static. These change with temperature, radiation, illumination conditions, and other things. So that's just something to keep in mind when you look at this curve. It's not a static curve. It's constantly changing depending on operating conditions. So now let's look at what happens when we connect the DC to DC converter with its negative input resistance to the solar array. As you can see on this curve, the upper portion is the solar array characteristics that we discussed. The lower curves show the array resistance versus the converter resistance. And you can see an inflection point where the converter resistance is above the solar array resistance for conditions above around 40 watts power from the array, and things would be reasonably stable here. Things would operate and the converter could deliver its power and there'd be no loop stability problems. But if you go to the left side of that inflection point, below 40 watts, the array can no longer provide all the power that the converter demands, and now you're going to see an unstable condition where the voltage on the array will collapse, the power will be greatly reduced, and the converter will no longer be able to stay in regulation and provide any reasonable power to its load. So what's SOLO, and how does SOLO work to fix this problem? Well, SOLO has two types of sweeps, and these are periodic sweeps of the DC to DC converters PWM ramp. So we have a large orbit, which is done more infrequently to find the global peak of the solar array, because recall the solar array could be many strings, many body panels on a spacecraft or something like that, and it could have multiple peaks in its power curve, and you want to find the highest peak. So you do a large orbit to find that global peak, and then you do small orbit scans around that large orbit peak. So the large orbit peak would be done very infrequently, let's say once every 10-15 minutes, depending on what your dynamic situation is. And then these small orbits could be done on the order of every 30 seconds, every minute, or something like that. So here in this curve, I'm showing the concept. You can see the solar array voltage with a large disturbance and then a smaller disturbance. And this system is a perturb and observe system. So that's what we're doing. We're perturbing the solar array, looking at the reaction, and we measure the peak current, the peak average current in the battery to see where the peak power point is. So you can see the solar array voltage with its periodic dips here. You can see the solar array power going up and down as we do the sweeps. And then you can see the DC to DC output voltage with its variations as we do the sweeps. Here in the bottom curve you see the solar array current. The first sweep is a major sweep looking for that power peak, which is around 850 milliamps it looks like. And then we repeat that with a smaller orbit and the next disturbance. Now what I've shown you here is the solar array current, but what you need to realize is what I'm really measuring is the battery current, and it's showing that I'm finding the peak power point by looking at the average current from the battery. So let's look at the large orbit response. Here we have the solar array voltage, the solar array power, and the DC to DC output voltage showing the large orbits during a large scan that we would do periodically looking for global peaks. So you can see how it orbits around the peak power point with a fairly large disturbance to find that first major. You can see that these orbits are going around the peak power point shown on the earlier voltage current characteristic curves of the solar array. So if you want to just take a moment to look at this plot and the units on the axes for the y and x and compare that to the VI curve for the solar array, you can see that we're tracking the power point. It's in the middle of those orbits. Now that we've found the global power peaks, we go into the higher rate small orbit scans shown here, and you can see the PPT voltage and current, and you can see these are very small deviations, around 41 to 41.8 watts and 50.2 to 48.2 volts. So those are fairly small orbits. These are arbitrary in my design that I'm showing you here. I can make them smaller. We can improve the performance, but this is a very simple design, very simple simulation that I'm showing you. Here we show a blow up of the small orbit performance as regarding the solar array voltage, current, and power, and you can see the average numbers there, and recall that the characteristic points of the array were 48 volts max power, 864 milliamps max current, max power current, and 42 watts max power. So I hope you found this useful. Everything you've seen here was simulated and built in TopSpice. You could easily do this in MATLAB or MathCAD or some other programs that you might like. And in the future I'll present more details, share the models, and show you how to do your own designs. Thank you.